read a paper the other day from a couple of gentlemen from merry old England, and I'm going to be analyzing their paper today. So let's see how it goes. And so this is the paper I'm talking about here. I summarized it from actually from a article as well as from their paper. Okay, and then here it goes. Mathematical physicists Joseph Aziz and Richard Howl are investigating whether classical gravity could induce quantum entanglement. In other words, they're trying to unite or somehow merge or relate quantum mechanics with general relativity. That's the bottom line. What's the thing they're working on? Gravity. That's what they're trying to figure out. Quantum theory postulates that entanglement occurs via the exchange of virtual gravitons. We used to have virtual photons, virtual everything, and now we have virtual gravitons as well, you know. And as space.com explains, these gravitons don't really exist. They don't exist. So these people are working on stuff that doesn't exist, right? But due to the wacky world of quantum physics, no, absolutely not. It's not a wacky world of quantum physics. What it is an irrational world of quantum physics. And the word physics is too large. It's the irrational world of quantum. Okay, it's black magic. That's what it is. That's what they do in quantum mechanics. Such particles are mathematically allowed for an extremely limited amount of time. In other words, this is mathematical gibberish there that has nothing to do with physics. All they say is, you know, we have some left over and we're going to call that a virtual particle. And this particle only lasts for a very brief period of time. And then, as I explained last week, these particles go into unseen dimensions, as good old Brian Cox would say. There could be virtual matter processes associated with a gravitational field. The gravitational field interaction could still potentially entangle matter. In other words, they're saying that, you know, entanglement is something that really belongs to quantum mechanics, and they're going to try to merge it with the classical, as they call it, classical gravitational field. Okay, they don't know what a gravitational field is, how it works, but whatever it is, they're going to get entanglement somehow, you know, because they're both action at a distance. They're going to try to merge them somehow. They just say that mathematically they're going to try to unite them, merge them, relate them in some way. There'd be methods for distinguishing between these two methods of entanglement. Quantum gravity would have stronger correlations than classical entanglement. Okay, so that's essentially the setup. This is what these people are trying to do. They're trying to merge entanglement somehow with quantum, really classical gravitational field. They have no idea what either of those is, how they work, but whatever they are, they're going to try to merge them. That's what they're trying to do. Okay, and so what they're proposing is really a test of some kind. Some experiment says, place a massive object in a quantum superposition of two locations and let it gravitationally interact with another mass. Okay, they're going to put two objects, right? And they're going to see if they interact gravitationally. And they have to be in this quantum superposition, meaning they're somehow one affects the other, right? If the two objects become entangled, right? If one object affects the other one at a distance without anything in between, right? This is unambiguous evidence that gravity obeys the laws of quantum mechanics. A classical gravitational interaction is a local interaction capable of only transmitting classical, not quantum, information. So these people are going to be transferring information. That's what they work on. In physics, we don't use the word information. We have nothing to do with information. But these people take this concept called information and they transfer it to each other. They play ball with it. The classical gravitational interaction can generate entanglement through physically local processes. Okay, so this is what they're proposing. They're proposing an experiment that should be able to tell you something about entanglement, something about the classical gravitational field, and with that they hope to figure out, I guess, gravity. They've gone through all this stuff. It's unbelievable where we ended up today after 400 years of mathematical physics since the days of Newton and even before then Galileo and so on. Okay, so who are these two fellows? Well, they come from a royal institution of some kind, Royal Holloway it's called. And it's a University of London, and it's a public research university. What does that mean? It means they receive government funds. They are supported, partially at least, by the government. In fact, I guess they cover approximately 1/3 of the expenses of some of these colleges. And I don't know how much exactly they cover for the Royal Holloway. These people don't really publish their numbers that well. They just receive the money and that's it. And so who is this Joe Aziz? He's investigating how quantum information, right? Techniques can be used to probe the nature of what? Gravitational interactions in quantum systems. And this involves what? Exploring entanglement. Okay, so he's going to do something with information, with gravity and entanglement, whatever those are. They don't know, but that's what they work on. They just put equations there and simulate things on their computers, and then this is what they get paid for, big bucks. And these people are maintained by taxes, essentially, in great measure. Some of them receive private grants or private institutions, but a lot of that comes from, the government. That means you're paying some of it at least, right? And what does Howl do? Besides howling, I guess, when he receives his paycheck. Researches connections between quantum information. Again, these people deal with information, whatever that is, theory, and high energy physics. How ideas of quantum information can be used to test quantum gravity. Again, they're going to be using information and relating that to gravity, and somehow they're going to bring entanglement in there. The bottom line, I think, is that they see entanglement and gravity as action at a distance, forces, phenomena, whatever you want to call them, observations, right? And so they think that maybe since they're both action at a distance, meaning black magic, that's, action at a distance is the term mathematicians use for black magic. Okay, but they don't call it black magic because people would say, what do you mean you're using a magic wand? No. What they do is they call it action at a distance. And people say, oh, that's so scientific. Yeah. Okay, let's see if any of this that they do holds any water. Okay, let's see what happens here. Here we have the fields, and we have the quantum field, bunch of particles, that's what it is, right? And you have the relativity field, the one from general relativity, and those are number lines. So you have all these number lines and you have all these particles, and the question is, how do you merge these? Remember, what a field is. Field is defined as a region of values, essentially. There's a value at each point in space. And you can see on the left there that they have, your Cartesian coordinates, as they call them, and they don't put numbers in there, and they don't put, the ordered pairs. But that's what those points represent. Each dot there is an ordered pair, a location of an ordered pair. And that's what they do later on the upper right-hand corner, where they start shaking all these, saying that all these little fields, pieces of fields, right, are vibrating. And each one of those is a particle. That's how they understand it mathematically, okay? Physically, you cannot even conceptualize what they're talking about because what they're doing is vibrating numbers. And again, none of that has anything to do with the relativity field, which is the warping of number lines, the shaking of number lines. So, how do you get these two things to merge, to fit together? And one of the things they do is this. They put it what is called virtual particles. This is the way they unite them. They kind of merge them. They say, look, we have the vibrating number lines, and then what you have superimposed on that are these virtual particles that come in and out of existence so quickly that they cannot even measure them. Okay, so this is what they represent mathematically, and this is how they represent it pictorially. Okay, so this is what they have going through their minds. This is what they're working on. And the question is whether any of this has anything to do with physics, with science, with reality, with anything. I mean, what are these people working? What do they get paid for? Okay, that's the question. And so here we can look at few ways that you can pull, because gravity is a pull force as far as everybody is concerned, and that follows from Newton's gravitational equation. Okay, these are the mechanisms you can probably, or that have been thrown around. The one on the upper left is the one that mathematicians use. They do use all these abstract concepts such as field and energy and information, and that's what they use to pull. Okay, somehow they put negative momentum or whatever in there, and they get away with murder as far as the mechanism is concerned. The one on the bottom left, the transverse waves there, I don't know how you pull with those, but they talk about, the gravitational waves, and we're assuming those are similar to the photon, light waves, unless, they have another notion for it. But again, if the wave goes outwards, how does it pull inwards? Okay, that's the question you got to think about. Then you have the particles on the upper right, and yeah, we cannot imagine throwing particles at a donkey and attracting the donkey. It just doesn't work. We tried it many times in the in the lab, in the field. We throw rocks at the donkey, and the donkey runs away. That's the way it really works. Okay, that's our experience. And the only one that really can work is if you put something, an elongated object between the cowboy and the donkey. Then you can pull. Okay, and in this case, we represent that with a rope. So yeah, the only way you can pull is if there's something between two objects. You have two particles, one is pulling on the other, there's only one way. There's got to be a mediator between them, a physical mediator. And no mathematician ever discovered this. Why did they discover it? Because they never thought that there were invisible, intangible mediators out there that Mother Nature and Father Universe use to do their daily work, gravity specifically. Okay, so here you have the virtual particles. How do they attract? These people say they exchange virtual gravitons. That's what they are proposing. And okay, so we have the cylinder sending these blue particles to the cube, which is sending the red particles to the cylinder. Okay, so we have rocks flowing back and forth. How does this attract the cube to the cylinder? We cannot conceptualize it with what these people are proposing. Okay. Now, a couple of weeks ago, I proposed what Arvin Ash, mathematical physicist, proposes, and he got that, I guess, from somewhere else. But what he proposes is the boomerang mechanism. And yeah, it's worth looking at this, because if you want to have a good laugh, right? Or if you want to have a good beer after this. Okay, here goes.
Imagine two people in boats tossing a ball back and forth. Each time the ball is thrown and caught, they push each other apart slightly. Now imagine these two same individuals throwing boomerangs to each other. Each time they do that, they move closer together. Virtual photons are like invisible balls and boomerangs exchanged between magnets, resulting in attraction or repulsion. This virtual photon exchange is something that all charged particles do. That's what a charged particle is.
Okay, got it? Boomerang goes from the outside and pushes. It's all push, according to them. They never discovered the force of pull in all of mathematical physics in the last 10,000 years, since the days of Pythagoras and Plato and all these people. They never discovered the force of pull, because in order to have pull, you have to have between, not from the outside. And they never were able to do that with particles, which is what mathematical physics deals with. Each particle represents actually a value. That's the way they look at it. Okay, so here's the two mechanisms, the one that quantum proposes. And okay, even if we concede that gravitons attract, what does that have to do with the mechanism that relativity proposes, which is warp number lines? I mean, these two mechanisms are completely different. How are you ever going to merge them if they're conceptually different? They have nothing in common. Okay, so even if the gravitons are true and we prove them and we certify them or whatever, we still cannot merge it with relativity, which according to the mathematicians, it's all been confirmed. Okay, so we have a problem on the gravity side. How about on the entanglement side? Well, here's the entanglement. This is what entanglement is, one particle affecting another one from a distance, right? And this is more or less how they illustrate that. You'll see this in many places. Okay, and what I want you to focus on is that green thingy that's between the particles. They put that in there by hand, okay? And the question is, yeah, it's logical if you have something elongated that stretches from one particle to another, but what is that? I mean, they put that in there by hand. They never identify what that green stuff is. And they put that in there so that you believe, right, that entanglement is a fact, meaning it happens. Yeah, that it does happen. Something's happening. But whether this is the explanation for that is a different matter. I mean, are the two particles connected or not? You know, again, that looks like my model, really, not like the mathematical physics model, because if you look at the standard model, you will not find those green lines in there anywhere, okay? And so the question is, what is that? What are they made out of? What is that green stuff made out of that, unites these two particles or keeps one somehow bound or affecting the other ones somehow, okay? And so let's see, here are the mediators, right? What are those green mediators? That's what I want to know, okay? Has anyone identified those ever? And, you know, here, if we're going to go with the particle and the waves that all these people use, waves in space-time, let's replace them with that. There we have. Is that what's keeping the two particles together? The number lines of space-time number lines, or general relativity number lines? Or how about the particles on the right-hand side there? Is that what's keeping them alive, one tied to the other? And again, if you have these particles, they're discrete particles, how does that attract? How does that keep one particle bound to the other so that they can roll around each other? And yeah, they'll never explain this because they never conceptualize any of the mechanisms that they're analyzing. They just mathematize them. They just go in there and they say, let me do some math on it, some equations. Okay, so what does that tell us about, the mechanism? And so, here you have entanglement. The question is whether you can merge that with a quantum field, okay? Or with, for that matter, with the gravitational field of classical mechanics. You have an asteroid falling towards the Earth, right, through this field, which are a bunch of vibrating numbers. That's all they are. They represent them with particles, okay, fine. So even if that were true, how do you merge that with quantum entanglement? I mean, what does the left have anything to do with the right? That's the question. Okay, so what these people are doing is just wasting a lot of space-time. It's called money. Okay, so they're wasting a lot of space-time. Okay, so how do we do it in science? Okay, that's the way we do it in science. The first thing we do is we get rid of the infamous transverse wave. Okay, these mathemagicians, as I call them, these people came up with the electromagnetic wave. What is a wave? Well, it's a couple of fields, and each field is a bunch of vectors. And what are vectors? Just numbers. Okay, what are electric fields and magnetic fields? They're also numbers. And what is a wave? A bunch of numbers. And the problem is that you see it on the bottom, they have all these vectors, these numbers, and they're moving from left to right. Very scary stuff. Okay, so yeah, this is what they came up with. And this is great mathematically. It's got nothing to do with reality. There is no such thing as a wave. There's no such thing as a field. There's no such thing as a vector. Okay, those are concepts. Those are mathematical concepts. That's what these people work with. Okay, and so what we did was replace that. Okay, we replaced the famous wave with a rope. Okay, it's called a two-strand rope, DNA-like rope. Okay, and now we have a physical object for the first time in physics. Now we can start doing physics. Okay, we have a rope and it torques, and that torsion is what we call light. And we're going to use the same rope, this mediator, this physical mediator, to do gravity. Okay, we don't need any entanglement, action at a distance, entanglement, action at a distance, gravity, any action at a distance. There's a physical entity we cannot see or touch. That's what it is. We could not see this object. An object is not that which you can see or touch. An object is that which has shape. The rope has shape, but you cannot see or touch it. Okay, and one thing that this thing answers immediately is the speed of light. You know, torsion's the fastest thing imaginable. And it's not just fast, it's the fastest thing imaginable. That's why it's the speed limit of the universe. And it also tells you why the speed of light is constant, because if little c, 300,000 kilometers per second, is equal to frequency times wavelength, well, that's the equation of a rope. The more you torque a rope, the smaller the shorter the links, and the more links you have. So the more links, frequency, and the shorter links, that's your wavelength there. And it's very easy to even to explain it to a 10-year-old, you know. Here's my famous rope, okay? And there you have it, okay? The more you torque it, the shorter the links, okay? And you have more links. And the more you untorque it, well, the longer the links, and guess what? You have fewer links. We're done. Any baby can understand that, okay? How are the atoms constructed? Because that's important to fit in there, right? Here's the atom being constructed. You have the electric thread. And again, electric and magnetic, we use those words simply to deal with convention, you know, just to follow convention. But you have the magnetic thread going around and encapsulating the proton star. Okay, that's what you see there. Okay, so the electron is a shell. It's a physical membrane that encapsulates the proton star. You can see the ropes end at the electron shell. Okay, so there you see it one more time. Okay, one thread goes right through the center to the other side, and the magnetic thread rolls around, okay, and encapsulates the proton star. And you have all the atoms in the universe are physically connected. They all end at your atom. All the ropes end at your atom, and all of them build your atom. Okay, so that's what we're showing there. Okay, so here we have comparison, right? Here you have the quantum atom, which is this planetary model they concocted. Niels Bohr and Heisenberg and Born and all these people. Okay, they went out there, and this is the ridiculous thing that concocted. And it's ridiculous because, you know, they set out to find out why the electron does not fall, bead, right? Does not fall to the nucleus. I mean, if the electron bead is rolling around, why doesn't it lose energy, as they called it, and fall, especially if the electron is negative and the nucleus is positive, why does it fall to the nucleus? And if that's not the case, why doesn't it spontaneously fly away? So it does neither falls nor runs away. It just circles and falls back and forth between energy levels or orbitals or whatever they want to call it. And there you can see at the bottom the R atom, and what it is the atom pumps back and forth. That's the quantum jump. By doing so, it torques the rope, and it sends the signal known as light. And you can see because they are physically connected, because the rope runs into the atom. Because of that, we can explain gravity, because now we have a mediator between the two atoms. Okay, any two atoms, they're connected by a rope. Okay, so that's right there. Now let's go to this. We have an example, how this works as far as gravity is concerned. We have the astronaut, he falls to Earth. Every atom in his body is connected to every atom on Earth and vice versa. Okay, so there you have it. He falls. Okay, and why? Why does he accelerate? Because the ropes fan out. The closer you get, see, the far away, they all form a single coaxial, like on a single axis. And as they come to the Earth, as the astronaut approaches the Earth, remember it's a distance squared phenomenon, the denominator. What you have is, acceleration of gravity. That is the acceleration, more and more ropes. So we should be able to illustrate, the weight of the astronaut at different heights, at different distances from the Earth, just by counting the number of ropes that are connected at that location to every atom on Earth. Okay, and so here let's illustrate that in a different way now. We're going to have a cube and a cylinder, okay? And the question is, this is what we see. We don't see the ropes, okay, because they're invisible, intangible. Okay, so this is what you see, and there you have Newton's gravitational equation. Okay, so what happens? Now we have God's eyes, suddenly we see the rope. Okay, and what we see is that all these ropes from all those atoms are on the same axis. They're all on the same axis connected to that red atom in the cylinder. Okay, that's what we're showing here. So they're all superimposed. Okay, and what happens? Remember, it's a distance phenomenon. They have distance squared in the denominator. What happens when the distance decreases? Well, when the distance decreases, you get this situation here. See if we can illustrate that. Okay, here goes. Here goes. Okay, you can see what's happening there to the ropes. Okay, they fan out. Little by little, you can see how they're fanning out, and you have more and more effective ropes, as we call them, and that is right there an illustration of the acceleration of gravity. Okay, that's why things fall faster and faster during gravity, any gravitational phenomenon. Okay, so there you have the mechanism that we propose. Okay, and here we have, you might say, where did you get this nonsense about, all atoms being connected by ropes? DNA like ropes. Okay, so let's find out here. We'll get some authority to bear on the subject because people believe in authority. And here we have good old Richard Muller from Berkeley University. He'll tell you why. Okay, listen to him carefully. This is not me talking. Okay.
If you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. You're pulling on atoms right now on the other side of the Earth. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay, so every atom in your body is pulling on every atom of the Earth. Every single atom of the Earth, and every single atom of the Earth is pulling on every single atom of your body. What part did you not understand? mass divided by distance squared. It's amply proven, verified, experimented, experienced, etc. Phenomenon. Okay, and one thing that allows us to explain is something that good old Albert Einstein was not able to explain, and that is the principle of equivalence, the reason, the cause for it. Here it is. Listen carefully. This is me talking in the background.
Every atom that comprises the Earth is physically bound to that atom. Therefore, it doesn't matter whether the atom is escaping from the Earth or falling towards it, or whether it's part of an elephant or a feather. The number of effective ropes converging on that hydrogen atom from Earth at that location is the same.
So what you need to understand is what gravity is. Gravity is, when we look at Newton's equation, it's a force. And what do we represent? We're representing weight. That means that for every location in the universe, wherever you are, it doesn't matter, you have a certain weight with respect to some object, some celestial object. And the closer you get, the more you weigh. That means that every location, your weight changes instantaneously, as soon as, to use that term, right? As soon as you move to a new location, you have a totally different weight. And so gravity travels at the speed of thought, so to speak. You move, you already have a different weight. Why? Because all the ropes change. Suddenly you have more ropes. So it's a rope phenomenon. And we should be able to illustrate the number of ropes converging on an atom. That's something we can conceptualize. We can illustrate it because we can conceptualize it. Okay, and as a bonus, we can also explain this thing they call entanglement. And there it is. Mother Nature doesn't understand positive, negative. She understands clockwise and counterclockwise. And so, when with a rope, you can explain that very easily, because from your end, let's see if I can get that right. There. From your end, from my end, it's going counterclockwise. Hopefully from your end, it's going clockwise, okay? And if we turn it around, go the opposite direction, again, now you have counterclockwise and mine is going clockwise. We're done. We have EPR with an elongated mediator to explain why, we have this phenomenon that the mathematicians cannot explain. All we needed to do all these years is figure out the word object. What is a thing? No mathematician ever defined it. No textbook of physics begins by defining what a thing is, what an object is. And it turns out you can't do physics without an object. No one even thought about defining this crucial word. And of course, they didn't define the word exist either. And everybody talks about existence because physics is the science of existence. And nobody defined the word exist either. And that's why all these atheists and theists and agnostics, they go around in circles talking about exist, whether God exists or not, because they never defined exist. And that's a summary for these two gentlemen who are wasting your money. That's what they're doing. They're wasting your space time.